Good morning, everyone. I'm Boxin from Arizona State University. Welcome to this presentation. I'm glad to be here to present our recent work. First, faster interactive attribute subgraph matching. Our title is first, so I'm the first one. Pretty fair. So attributes and networks are everywhere. We list some examples here from our familiar social network, like Facebook and LinkedIn, to the financial networks like stock correlation network and Bitcoin transaction network. All those real-world networks come with both a node attribute and an edge attribute. The question is how to explore those attribute subgraphs, attribute networks. Sorry. One answer would be to use attribute subgraph matching. So what is subgraph matching? Subgraph matching, the goal of subgraph matching is to find substructures to your interest. For example, given this LinkedIn network, we call it the data graph. Our user might be interested in building a team from this data network. For example, if he wants to build a team with one accountant, one engineer, one manager, and one market investigator. And he wants every one of the team communicate with each other. And we call this kind of structure a query graph. During his search, he may find substructures like this. It matches with the query graph. It means not only the structure of this substructure, but also all the attributes matches with the query graph. We call this kind of matching an exact matching. Also, he may also interested in subgraphs like this. It has 4 nodes that matches with the original query graph, but there is 1 extra node and 2 extra edges. We call this kind of matching inexact matching. So during subgraph matching process, our user might be interested in both exact matching or inexact matching. There are some more applications about attribute subgraph matching. For example, like to find the chemical substructures. As we know, certain chemical substructures corresponds to chemical properties of a compound. It helps us to discover the chemical properties of a compound. In the protein-to-protein interaction network, the PPI network represents the physical contact interactions between proteins. So certain, like we see here, certain pathways or patterns reflects the interactions between protein molecules and how they function with each other. And in the fraud detection test, if certain fraud patterns is known, we can detect fraud patterns from this financial network. And also in our familiar social media analysis, certain graph patterns corresponds to social patterns. And the list goes on and on. There's so many applications. We listed some methods from the recent literature. Actually, there are so many. And from our observation, some methods may only support exact matching or not inexact matching. Some only support node attribute but not edge attribute. But almost all the methods does not support a vague query, or they require user to provide an accurate query. What does it mean? So what if the user does not know exactly what he is looking for in the very beginning? The user might only have a vague idea or only sure about part of the structures of their queries. So the queries might be changed frequently along the way of the searching. Also, we want to find a method that supports both inexact matching, node attribute, and edge attribute. We introduce interactive subgraph matching with this example. So given a social network here on the right side, all the node attributes and the edge attributes. The colors and the shapes of the nodes represent the node attributes. Here, it represents the skills that the people have in this social network, and the edge attribute in this social network represents the there are communication methods. For example, like face-to-face or email or phone. So what is the interactive process? So given this initial query, it's a 3-node line. Here is the initial matching graph. And the user might want to change the query because there are 2 people with the same skill set. So he may want to change the query like this. For example, he wants to add another skills to the team, and he wants everyone in this team to communicate with each other. And then here is the updated matching subgraph. And also he might want to add another one with another skills to the team. And here is the updated matching subgraph. As we see, this is an inexact matching graph with 3 extra nodes. The user might think that, oh, there are too many members in the team. He doesn't want to do that, so he wants to simplify the query like this. He deleted an edge. And here is the updated matching subgraph. So this process is we call interactive attribute subgraph matching. The challenge is how to respond efficiently, because of course we can rerun the algorithm or we can rebuild the graph indexes like our previous method do, but considering the efficiency, this is the last thing we want to do. Then we're going to introduce a problem definition, and we propose a solution called first, it's a family of algorithms, and we provide our experiment and conclusion. So this is our formal definition of this problem. So given we have 4 inputs here, so an undirected attribute subgraph G, undirected initial query graph Q, an initial matching graph M, and our revised query Q tilde. Our goal is to efficiently find the updated matching subgraph M tilde. We have 2 ideas, and I'll provide some details. The first idea is we want to recast the matching problem as a cross-network node similarity problem. The reason we want to do that is because by using cross-network similarity problem, we can encode both the topology and node and edge attribute into the matching problem. Also, it turns out that our major computation lies in solving a Sylvester equation. And the second key idea is to explore the smoothness of query graphs, because we want to incrementally solve the Sylvester equation, but by exploring the smoothness of query graph, we can do this. And we actually, based on our observation, we find that the revised query can be viewed as a perturbation of a previous query. I'll explain this later. So the first key idea, the first step is to find the similarity matrix S. To do this, we adopted a recent network alignment method from KDD 2016. And the major computation lies in solving this Sylvester equation. A W is a Kronecker graph of G and Q, filtered by node or edge attributes. I'll explain this later. And actually, based on whether or not the node or edge attribute is available, the W can take 3 forms. S is the vectorized similarity matrix, and the H is the vectorized preference matrix. So the similarity matrix looks like this. Taking our previous example here, we have a 3-node query and 12-node data graph. S is a 3 by 12 matrix, and with Sij represents the similarity scores of the ith node in query Q and the jth node in network G. And the H basically has the same dimension with S, but it represents our previous knowledge of the similarity score. So the second step is to find the actual matching graph. So our idea is to first find a permutation matrix. One permutation matrix corresponds to a set of matching nodes, and then we want to generate the actual subgraph. And how to do it? We adopted a goodness function here, g of x. The intuition behind g of x is we want to measure how close the matching subgraph is to the query graph. We have three terms. In the first term, it measures the network connection of the subgraph. Basically, it measures how close our matching subgraph is to the previous query graph. In the second term, we measured the similarity score. We take the summation of the similarity scores of the matching nodes, and then we measure the quality of the individual matching nodes. And in the third term, because X is a permutation matrix, we want it to be orthogonal to its transpose. And we want to calculate X by maximize this goodness function. This is our idea. We summarize the first step by using this pipeline. We first took the Kronecker graph of a query and data network, and it was filtered by the attributes. We solve similarity vectors by solving the Sylvester equation, and we solve the optimization problem to get matching indicator matrix X, and we generate the actual subgraph by a heuristic local search method. So much for key idea 1. So what about key idea 2? The first row is taken from the previous slide. The second row is basically the same procedure, but with different queries. So we observe that the revised query can be observed as a perturbation of the previous version because as we see we add only one edge and we change the node attribute of one node. But we might ask the question that, would it be the situation that the W or S also be the perturbation of its previous version? So because our data graph keeps unchanged, if that is the case, we don't need to run the whole process again. We only need to, but we can solve it incrementally. I'm going to provide some. Oops, sorry. Excuse me. This is some details. Actually, like we discussed before, based on whether or not node or edge attributes is available, W can take these three forms, and N and E are node attribute matrix and edge attribute matrix respectively. We can filter our Kronecker graph by these two matrices. Our first scenario is we assume that during the query revision, only graph topology is changed. Our goal is the fast computation of similarity vector after topology revision. So from our observation, we can see that actually we can speed up the computation by calculate the approximated version of similarity matrix. But we don't have to do it. We don't have to approximate the W matrix directly because we can do it in a pre-computation stage and speed up the computation. Like we said, we can make use of the smoothness of the query graph. So here are some details. We adopt the low-rank approximation in the pre-computation stage, and we can use this. We can store this result and use this result in constructing the approximation of W matrix in the interactive stage. The results shows that both time complexity and space complexity scales linearly with regard to the dimension of the data graph. Here, N is the number of nodes in the data graph, and M1 is the number of edges in the data graph. Our second scenario assumes that during query revision, only node attribute is changed. So we observe that in this scenario, based on the first scenario, both the data network and the query network can be approximated in the pre-computation stage, and we only need to construct the node similarity matrix, a node attribute matrix in the interactive stage. So Still, we used a two-stage algorithm, and we used a low-rank approximation here. Here are some more details. As we see the dashed arrow, actually the both query graphs and the data networks can be approximated in the pre-computation stage, and it can be used in the interactive stage. The results shows that the time complexity and the space complexity still scales linearly with regard to the dimension of the data network. And actually, because we used the approximation in the pre-computation stage, this further speed up this algorithm. In scenario 3, we assume during the query revision, only edge attributes are changed. So our goal is to have a fast computation of similarity vector after edge attribute revision. We observe that different from the first two scenarios, we might have many edge attributes here. So instead of approximate the original data network, and we want to approximate the edge attributed adjacency matrix, and there's a series of them. So we can do this in the pre-computation stage and interactive stage. We only need to apply those approximation for those revised edge attributed agency matrix. So here are some more details. As we see, the construction of W matrix is by U and lambda. They are a block matrix, and the bricks of constructing those two matrix can be retrieved from the pre-computation stage. Still, the times complexity and the space complexity scales linearly with regard to the size of the data graph. We show some experiments results. We used 5 real-world graph data sets with number of nodes ranging from 9,000 to 6 million. We adopted 3 baseline method. 2 of them are subgraph matching method, and one of them is a network alignment method. First, we test the effectiveness of our method. We used 5 typical query graphs. They are a star, elongated star, line, loop, and click, like we showed in the left side. We tested the percentage of exact matching nodes. So higher is better. So we can observe that generally our method can generate more accurate matching subgraphs. And after that, we tested the percentage of extra nodes, and we tested the percentage of exact matching edges, and the percentage of extra matching edges. From our observation, our baseline method might perform also very well in one matching queries, one type of queries. But it's not the case in other types of queries. This is the case when we test other methods. Our baseline methods may deviate significantly from various queries, but from our results, our method generally can generate more accurate results. We test the efficiency. The yellow bar is our method, and the blue and the green bar is our baseline method. The vertical axis is the log of running time. When we tested on 6 million of data network, we achieved more than 15 times speed up. When we add edge attribute and tested it on the 5 data set, we achieve more than 7 times speed up when we test on the 6 million network. Also, we tested the efficiency with regard to the size of the query node. Our method scales linearly, as we see here. And we conducted some case studies. This one is on DBLP dataset. The first row is our query graphs, and the second row is our matching subgraphs. The yellow rectangle is the matching, is the matching nodes, and the white rectangle is the intermediate node. The green circle represents the node attributes. To conclude this presentation, our goal is to find efficient methods for interactive attribute subgraph matching. We proposed a family of algorithms called FIRST. The first key idea is to recast the matching problem as a cross-network node similarity problem. And our second key idea is to solve this problem by explore the smoothness of query graphs. Our result shows that our method scales linearly with regard to the size of the network, data network, and also query. And also, our method has better query matching graphs against our baselines. Thank you.